thermodynamics, utilization of solar energy. He is working as professor in National Institute of Technology, Warangal, and he worked as lead CFD engineer in General Motors Technical Center, Bangalore. Sir, research projects are visualization of carbon particle tracking and hydrogen production in a vertex flow solar reactor from Qatar Foundation and ITS Research Computing Group, and where it is completed one. And next project, investigation of corrosion on metals with phase change materials for a 30 to 100 degrees centigrade temperature range solar thermal heat storage applications from MHRD NIT Warangal, and it is also completed one. Design and development of an efficient and cost effective solar water latent heat storage system from DST SIR project, and it is also a completed one. Internal flow fields analysis of solid rocket motors before and after sudden opening of thrust termination ports from DRDO Advanced System Laboratory, which is a completed one. PCM characterization and techniques from DRDO Combat Aircraft System Development and Integration Center, which is a completed one. And SIR's ongoing project is intrinsic convection and magnetism inside the Earth, planets, and fast rotating stars, new similarity criteria, scaling glass, and simplest methods from Spark, which is a worth of 74.04 lakhs. And Sir has a consultancy project titled Simulations of Lithium Ion Battery Pack for Effective Thermal Management from Axinos Solutions Private Limited, Chennai. Dr. Jayakrishna Devanuri sir has 3 granted patents. He is guiding 3 PhD scholars now. He has 3 book chapters, and sir has published 59 international journals, and he is the author of 35 international conferences and 9 national conferences. Now I request Jayakrishna sir to take over the session.
Thank you, ma'am. First, I'll be sharing my screen. Ma'am, are you able to see my screen?
Visible, sir.
Okay. Okay, ma'am, is it fine?
Yes, sir.
Yeah. I'll do one thing. Just 1 second.
Sir, it's visible, sir.
Yeah, 1 second. I just make sure that the screen size is big. Can anyone please tell me, like, are you able to see my screen, which gives the title of the workshop?
Title slides.
Yes.
Yeah. Okay.
Full
So, yeah, thank you. Now we are going to start our session. Before I start, I would like to thank Professor Vijay Kumar and the administration for giving me this opportunity. And welcome one and all to this faculty development program on emerging green hydrogen energy technologies for societal sustainability and climate change mitigation. So, and the title of my today's presentation is Production of Hydrogen Using Solar Energy, a Methane Cracking Perspective. Because we do have different methods by which we can generate hydrogen. But I'll be discussing more about how we can use solar energy, and specifically in that we do have one thermochemical method by which we can produce hydrogen. And I'll be discussing further other things also, what are the various other methods we can have. And towards your left, there are two methods. One is a Fresnel lens, and another thing is like a heliostat based central receiver system where we can tap the solar energy. And if we are not going for any renewable sources to tap energy, this is going to lead to severe consequences, which you can see towards our right. With this, I'm going to go with my outline of my presentation. See, like first I'll be discussing a few aspects of global warming and its consequences. I'll be going through it in a very brief manner. And why do you think hydrogen is required? And to get to tap hydrogen or to produce hydrogen, what are the various methods we have? In that, why solar? Why solar can be preferred? And that too, we are seeing the different hydrogen, like based upon how hydrogen is produced. We say green hydrogen, blue hydrogen, brown hydrogen, black hydrogen, white hydrogen, and so on. What does it actually mean? And specifically, what does green hydrogen mean? And in the process of producing hydrogen, we are going to discuss about methane cracking process. So why methane cracking process, and how does it work, and what problems do we have, and what are the various methods by which we can have different ways of producing hydrogen. And if it is so, still we are not going for this particular process. So it means like there are some difficulties. And what are the various available technologies that we have around the world, and what kind of problems that they are facing. And a new concept that is we did designed this kind of system, and we coined it as aero shielded reactor at Texas A&M. And finally, I'll be closing my session with the conclusions, brief conclusions. So the first one is like global warming. This thing might be everyone might be very much aware of. So we say like global warming, and this is because of CO2 emissions and greenhouse gases and so on. Just to tell in a very brief manner. So when these greenhouse gases in our atmosphere increases, it will not allow the reflected radiation to go into the space, because of which the average temperature increases. We say this thing as a greenhouse effect. So if you say about global warming, every time we just refer to CO2. But CO2 is not the only greenhouse gas that we have. I have given over there like it can be like water vapor is one greenhouse gas, nitrous oxide, carbon dioxide, methane, and so on. Now, but why we talk only about carbon dioxide? Why don't we project or mention about other greenhouse gases? The thing is, out of all the various other greenhouse gases that are available, carbon dioxide contribution is large. So it contributes to 60% of other greenhouse gases that are available. And next question is, are these greenhouse gases not available? So are we facing for the past, like especially facing these consequences because of severe increase in these greenhouse gases, especially for the past like 40 years or so, or a little bit earlier? The thing is, actually these greenhouse gases are available, but these greenhouse gases contribute only 1%. So what is going to happen if these greenhouse gases are not there? So if this 1% greenhouse gases are not there, our earth will be too cold to live. Something like whatever temperature we are having now, it will be something like 30 degrees centigrade less temperature we are going to experience. So our earth becomes too cold to live. So this nature is perfectly balanced by keeping the required things. But what we are doing is we continuously dump so much of these greenhouse gases, specifically CO2, and we are increasing this percentage of greenhouse gases that are available in the atmosphere. And because of which, what is happening is it is leading to several consequences, like everyone is aware of. So if rain comes, it is coming as a flood, or it is not like moderate rain, it is only a cyclone and so on. So obviously there is a need for us to seriously address this point. So now there is always a debate uh, throughout the world. Like one of the group will say like this is the tendency of the Earth itself. Generally, Earth's temperature increases, and it is a cycle. Gradually, the Earth's temperature decreases. So one proof was obtained by taking samples of ice near the poles, and what is observed is with the it is proportion the average temperature of the earth is proportional to the CO2 emissions, and you can see the graph over here. So with the increase in CO2 percentage, the average earth's temperature also started shooting up. This is one proof that we have, or that we can strongly say that because of increasing CO2 emissions, the average temperature is increasing. So this is one thing. If you just see from throughout the world, what are the various CO2 countries that release the CO2 emissions based upon the fuel combustion. So if you see, China stands first, and it is around 11,900 metric tons of carbon dioxide equivalent. Next comes the United States, and India stands third. Obviously, there is a significant difference between when you compare India with United States and China, the magnitude is very large, but still we stand third, and fourth place Russia, and so on. Obviously, the first five countries, if they significantly contribute, we are going to obviously reduce the CO2 emissions in a bigger manner, like a bigger scale magnitude. So let us see how it is going to happen, and how these emissions are, and from where these are emissions are coming, what is their source. So 4% is coming from gas, and 22% from oil, and 74% from Indian context, it is from coal. And if you see the world, rest of the countries that we have, so coal percentage is relatively less here, 47%, oil is 31%, and gas is 22%. Obviously, Europe is going for much cleaner fuels, and still India is relying on coal itself. So obviously, our reserves that we have for like a petrol and other fuels is very less. So we are now still depending upon this coal itself. But obviously, this coal, because of the fuel that we are using, the CO2 emissions are very high. So we need to focus on these things also, like better way or cleaner fuels need to be used. And if you see the renewable energy, electricity produced by tapping renewable energy sources, if you see none of the countries which pollute a lot, something like China, US, India, Russia, and so on, they are not in the list. And from Norway, 98.3% of their electricity production sorry, is from renewable energy sources. Brazil comes next, and so on. And if you take from India side, like if you focus on India alone, its renewables contribution is around only 22.2% for our electricity production. So there is we still need to increase the magnitude. So if you see throughout the world, if you just compare, renewables is only 29.9%, and non-renewables is around 70%. And if you see from Indian context, we just go for only 22% is from renewable energy sources, and remaining major chunk is from non-renewable energy sources. And especially we do have various renewable energy sources. Among this, most commonly or most widely used sources are nothing but wind and solar. Let us have a look on solar and wind perspective. So from as usual, especially the European countries that we have, Denmark, Netherlands, and their major production is from obviously solar and wind. And from Indian context, it is around 11.3 percentage. So if you see this one, wind from if you take throughout the world, wind contributes something like 7.5%, solar is 5.1%, and other is 87.4%. But from Indian context, like solar is only 6%, wind is 4.7%, and the other ways of tapping energy is 89.3%. So, but India is blessed with good solar radiation, and we are blessed with good coastal area also. So there is a need for us to tap these two wind and solar renewable energy sources so that our CO2 emissions can be significantly reduced. So there are several maps that were taken, and what it was observed is there is a gradual increase in Earth's temperature. Wherever you are seeing uh, red contour, so there is a increase in temperature, and year by year this is actually shooting up. So obviously when the ice near the poles melts, the sea level, there will be a rise in sea level, and obviously the land slowly will be covered with water, and slowly land also gets eroded, and this becomes a major problem for us. So and this is not the only problem. Everyone was looking about increase in sea level, but there was another study which is being carried out, and there are already certain proofs. What it was told is in certain locations like Serbia and Poles, there is a lot of viruses which got tapped under the ice. But because of global warming, whatever like viruses are other dangerous things which got tapped under the ice, because of the melting of the ice, this slowly started mixing in ocean water, and it is coming towards the human population. So that is why we are seeing like different diseases and so on. Okay, so there are two aspects. One is like raising sea level, and another thing is we need to be very much cautioned, or we have to take utmost care about various viruses and diseases that are coming because of the global warming. So there is a need for us to seriously look into this issue. And already from raising sea level point of view, so global sea level rose about 17 centimeters in the last century, and the rate in the last decade is nearly the double. So the rate at which the rise in sea level is there, it is very rapid. So maybe after a particular duration, we may not be seeing like Maldives in our map, because totally it will be filled with water. Now, what is going to happen? What kind of consequences we are going to experience? This is directly taken from UN climate change, official website. So, for example, if there is average temperature increases by 1.5 degrees centigrade, so then there is a 3% probability that Arctic area will be free of ice in any year. So in the same way, if you have that 1.5 degree C, then the average drought period can be for 2 months, and because of which 4% of mammals will lose their habitat. So in the same manner, if the rise in temperature is about 3 degrees centigrade, then there is a 63% chance that Arctic will be free of ice, and the drought period can be nearly 10 months, and because of which the 41% of mammals will lose their habitat. So this is again a very serious concern. And okay, now we could understand what are the consequences that we are going to have with these greenhouse gases and increase in pollution levels. Then what is the solution for it? So the solution for it is, if you go back and see our history, we started using different fuels. Let us see from calorific point of view. Right from the starting of 1800 and so, we started using wood. And if you just see the hydrogen to carbon ratio of wood, it is nearly 0.1. And slowly we started going for a fuel which has higher calorific value, or in the sense the energy density is high. Then we move to coal. Then we are going for oil. Now, or we are just going for like natural gas is a trend that is going on now, where hydrogen to carbon ratio is around 4. So in future, it is going to, we are going to totally depend on hydrogen. If you see what are the various fuels that we have, hydrogen is going to have the highest calorific value. So the energy density is very high. And one more thing is, obviously we can make use of devices like fuel cells where there is no CO2 emission at all. So now hydrogen can be considered as a future fuel, and this is one reason why the future is going to be hydrogen economy. So maybe around 250 onwards, 2050 onwards, the economy will be depend. It can be depend upon the hydrogen, and it can be projected as hydrogen economy. Now, if you see that, obviously, I did give like earlier one more curve. If you see like year by year, the CO2 emissions or carbon emissions are shooting up. So if you just observe, atmospheric carbon dioxide concentrations have increased. This is relatively a old data. Now it is further increased. It is much higher value now. Percentage is much higher now. So I thought of having a reasonable reference. That is why I have given the old reference here. So these are what, like, so we need hydrogen just to satisfy our energy needs. Along with that, we need to go for like cleaner ways of producing energy or power, or in other sense, electricity. So because of this, even if you see like, if you just take Government of India website, MNRE, Ministry of New and Renewable Energy, it has started National Green Hydrogen Mission. So what does it say? The National Green Hydrogen Mission, like, is initiated by Government of India to make India a global leader in the production, use, and export of green hydrogen. I'll come back to you. What do you mean by green hydrogen? So it aims in such a way that by 2030, that means 2030, uh, the green hydrogen production. What do you mean by green hydrogen? I'll come back again. So its capacity should be at least 5 million metric tons per year. So, and again, so what consequences we are going to have? So, because if we are able to achieve this, we can reduce nearly 50 million metric tons of CO2 emissions, that greenhouse gas emissions per year. So ultimately, the production of hydrogen can be directly linked to greenhouse effect or like global warming issue. That is why it is very much important for us to go for hydrogen production, or in the future it is going to be a hydrogen economy. So especially like has Indian government itself has allocated around 19,744 crores for national green hydrogen mission. So you can get all these details from MNRE website, like Ministry of New and Renewable Energy. So the magnitude at which all the like countries around the world are looking for green hydrogen can be understood from this particular point itself. So let us see, like, what do you mean by green hydrogen? What does green mean? So let us go through those details. So if you see types of hydrogen, in the sense, types of hydrogen means hydrogen is the same only, but how it is produced, depending upon that, several color codes are given. So I just mentioned even Indian government itself, like MNRE, you can see that in that website itself, they're saying green hydrogen, green hydrogen. So what do you mean by green hydrogen? Green hydrogen means if the hydrogen is produced with low or zero emissions, we say that thing as a green hydrogen. So what are the examples for it? And how can we say it is a green hydrogen? One best example is like electrolysis. Electrolysis is generally like splitting of water. When you split this water, obviously you'll get hydrogen and oxygen. And obviously use electricity for it. So, and you get electricity from various renewable energy sources like solar or wind. So, in this production of hydrogen, this particular process of electrolysis or green hydrogen, there is no CO2 emission at all. Or you can say it is like a negligible. Another thing, you can say it as a methane cracking. In this particular case also, there is no CO2 emission at all. So how it is going to be, I'm going to explain you in the coming slides. These processes emits zero carbon dioxide. That is why a color code, hydrogen, a tag of green is given just to mention in the production of hydrogen, there is no CO2 emissions at all. So what else do we have and what other color codes we have and what does it mean? I'm just going to explain you now. So the color codes that we have is green hydrogen, blue hydrogen, gray hydrogen, purple or pink hydrogen, turquoise hydrogen, brown or black hydrogen, yellow hydrogen, white hydrogen. So obviously one has to understand in the process of producing hydrogen, how it is made, what is the basic resource for it, and what about like CO2 emissions. Depending upon that, different colors are given for hydrogen. So obviously, I did mention about green hydrogen. Obviously, there is no CO2 emissions at all. Like you use energy sources like renewable energy sources like wind and solar, and in the production of hydrogen, you do not have CO2 emission. Next is blue hydrogen. See, blue hydrogen, you can even have steam reforming where you use methane and expose the steam. In this process, you will get CO2. That is one approach. But whatever CO2 you have by using certain carbon capture methods, okay, carbon capture methods, what you do is you again whatever carbon dioxide that is produced, you again reduce that, you again nullify it. So in the process, there is a CO2 emission. But the thing is, whatever CO2 that is emitted is again captured back. So you do have CO2 sequestration and carbon capture methods and so on. So we will make use of that particular methods, especially in blue hydrogen. Next is like a gray hydrogen. Hydrogen can be extracted from natural gas using one steam methane, in the sense we say steam reforming. So in this most common form of hydrogen is this is how hydrogen is produced as of now, like till date. So whatever hydrogen that is produced around the world is basically by steam reforming. So there is a need for us, obviously there is a CO2 emission in this. So there is a need for us to go in such a way that the CO2 emissions are nullified or reduced. Next is purple or pink hydrogen. Here hydrogen is produced by electrolysis only, but the power that you get, electricity that you get from electrolysis is from nuclear power. So then you say that thing as a purple or pink hydrogen. Turquoise is nothing but hydrogen produced by thermal splitting of methane. But here what happens is whatever CO2 that you get, it is in solid form. So this is the main difference. And if you take brown or black hydrogen, this way of producing hydrogen is the most polluting one. So you do like coal gasification and so on, but in this process, you do have a lot of CO2 emissions. So whatever we have to make sure the hydrogen production is in such a way that it has a minimum or like zero CO2 emissions. Along with that, we do have yellow hydrogen, we do have white hydrogen. Yellow hydrogen is also from electrolysis only, but this electricity you are getting from grid, and this grid, whatever power that you are getting from the grid, can the source can be any renewable energy source. Again, it can be like solar or wind or any fossil fuels. So ultimately you are using power directly from the grid. That is what it makes that thing as a yellow hydrogen. And next you have white hydrogen. Hydrogen produced as a byproduct of industrial processes, because during the process of particular industries, what happens is hydrogen becomes as a byproduct. So this kind of way, this approach of producing hydrogen is coined as a white hydrogen. Okay, so what you can see is out of all these color codes, the best thing that we can go to reduce CO2 emissions is green hydrogen. That is why if you see this one, Indian government itself is seriously looking into green hydrogen, and that is why they have started this mission, National Green Hydrogen Mission, and they are actually pumping a lot of money also to encourage, or like it is encouraging to work in this particular field such that you end up in having hydrogen in its greener form. That means with zero CO2 emissions. Okay, now what I suggest is like we do have various other like wind, geothermal, and so many other methods are there. Tidal power, ocean thermal energy, different ways of tapping renewable energy is there. But I would like to focus on solar energy itself. So why solar? So if you just take annual solar energy reaching the Earth's surface is around like 1.5 into 10 power 18 kilowatt hour. While if you just see the world energy consumption, it is about 1.5 into 10 power 14, which considers which can be around like only 0.1% of the solar incoming solar radiation. So if you are able to tap the solar energy, it will meet our requirement. It is satisfy all our power needs. But what happens is due to this reflection, absorption of these clouds and everything in the atmosphere. So on an average basis, you'll have around 1 kilowatt per meter square under ideal conditions. Obviously, if you have a cloudy day, it can be much less also. So then what is the problem in using this solar energy and get green hydrogen? But it comes with like three main disadvantages. If you see the power density of solar radiation reaching the Earth's surface is low. So you need to have some device such that you can tap this solar radiation. And one more thing, it is totally unpredictable in nature. So one of the drawback with renewable energy sources is it is unpredictable. Why? Because now let us take you have a very bright sunny day today, and suddenly maybe the next hour there can be a passing cloud, and there may be like a reduction in solar radiation. And sometimes wind can be there, or sometimes wind may not be there. So obviously, this you do have like a temporal variations for this one. And one more thing, like, so what is the problem for it? Like, what is the solution for it? So for the second one, you need to have a storage. So along with when you are tapping renewable energy sources, one of the very important aspect is energy storage. How effectively you can store energy, that much promising the renewable energy source is going to be. Another aspect, another third major disadvantage that you have is solar irradiation is unequally distributed over the Earth's surface. So it is not the same around the world. For example, from Indian context, south region it is something and north region it is different. In European countries, you can hardly find sunshine. So there are disadvantages. Like one is the power density is very low. There is a temporal variation. Another thing is like it is not equally distributed over the Earth's surface. So what are the solutions for it? So you make use of solar device such that you can concentrate the solar radiation and meet your requirement. To overcome the second problem, you need to have a conversion and storage system. Storage system can be of different forms. It can be electrical storage, it can be thermal energy storage, and so on. And another thing is transportation of the energy. So what you do is wherever you have solar energy, you convert into one fuel and transport this fuel to wherever you have very less solar radiation. Let us take, if you take Middle East in general, you do have, it is very much blessed with the solar radiation. And you take certain parts of Europe like Serbia, let us take Serbia. So there you hardly find sunshine. Now what you do is you tap the solar energy, convert into fuel, and by means of cylinders and so on, you transport this particular fuel to wherever you don't have solar radiation. That is what the third issue can be overcome. Now, if you just assume a mean annual solar radiation of 1700 kilowatt hour meter square and a collector efficiency of about 5%, the total area that you need is around 1100 kilometer square. So this corresponds to only 2.4% of the total surface. And if you take land alone, it is about 8.1%. Now let us see these problems one by one, how to overcome this and what kind of methods we can have. So if you see solar energy, everyone thinks that you can tap solar energy only by means of solar photovoltaics, but it's not the only way. You can even tap solar thermal energy and obviously again convert it to electricity. So I'll be focusing more about solar thermal so that it will be helpful for the topic that we are discussing. So depending upon concentration ratio, there are like non-concentrating type and concentrating type. So when you go for a flat type or like non-concentrating type, the temperature that you can attain will be less, and it is given by a concentration ratio. How do you define concentration ratio? Is it is the area of the aperture to the area of the receiver. So what happens is whatever radiation that is incident on some surface, if you are focusing at one particular point, so then you can attain very high temperatures. So more the concentration ratio, more the temperature value that, yeah. Next one, sir. 20, this one. So I'll just, I think here it was stopped. So different color codes are given based upon how hydrogen is produced. So like even if you have seen earlier in earlier slides that government of India is also going for green hydrogen mission. So such that while producing hydrogen, there is no CO2 emission at all. So in this particular presentation also, we are going to discuss about a methane cracking process, which comes under green hydrogen production. Can you go for the next slide, sir? Like after understanding like why hydrogen, how we can produce hydrogen by tapping renewable energy sources, and we do have various other renewable energy sources like solar, wind, biomass, geothermal energy, ocean thermal energy, and so on. But there should be a proper reason or some advantage for us, like to go for a specific solar energy, like solar renewable energy, which is nothing but solar. So what I can mention here is, if we are able to tap at least 0.1% of the incoming solar radiation, we will meet our energy demand that we have around our world, around the world. So, and also if you see like by overcoming, like if you consider the losses that we have by the absorption in the atmosphere, reflection, and so on an average, we will have around 1 kilowatt per meter square of solar radiation that is reaching the Earth's surface. And obviously, it will fluctuate. It is not going to be the same. It can be slightly less or more also. This is an average value. Can you go for the next slide, sir? Next slide, please. But the problem with utilizing solar energy or in general renewable energy, any other renewable energy sources, like it is a temporal in variation, temporal variation. Why? Because it is not continuously available and it is totally unpredictable in nature. So especially from solar energy point of view, we have like three major problems. One is that power density of solar radiation is very low, and obviously the incident solar radiation is not uniform throughout the day. It varies on a daily basis and seasonal basis also. And another thing is like whatever solar radiation we have, it is not equally distributed over the earth. So how we can overcome this problem is, first one, use some concentrating devices such that you can concentrate the solar radiation. Next one is like you convert solar energy and store it in different forms, like something like you make use of PV and have electrical energy, and you can store in terms of batteries, or you can store solar thermal energy, and so on. And the third major problem is unequally distributed over the Earth's surface. So what you do is, wherever, if you take some Middle East or so, like where you have good amount of solar radiation, so you make use of the solar energy and convert into transportation fuel like hydrogen, store in terms of cylinders or any other means, and transport to the location where you don't have solar energy. Like in this way, whatever three major drawbacks you have, there are actually solutions for it. And we need to march in this particular line such that we can effectively tap the solar energy. So if you just take on an average basis 1700 kilowatt meter square of solar radiation with a collector efficiency of 5%, you need something like 1100 kilometer square of area. And if you say like this comes to be around 2.5% of the total Earth surface, and again 8.5%, especially on the Earth's surface area covered with land. Can you go for the next one, sir? So in general, if you see, if someone says like about tapping of solar energy, we are very much used to say that only PV, but PV is not the only option. You can tap solar energy in the form of thermal energy and use this thermal energy to generate power. So next one, sir. So there are there are different ways or like devices, or like in short we can say it as like collectors. It can be of concentrating type and non-concentrating type, and you can say in terms of like more the concentration ratio. And how do you define concentration ratio is area of the aperture to the area of the receiver. So if your temperature requirement is high, you definitely go for a concentrating collectors, where when you have more concentration ratio, the temperature range can be higher. For example, if your concentration ratio is around 1000, you can still reach something like around 1000 to 1500 degrees centigrade. So this is basically to give a snapshot of obviously based upon your requirement, you can go for different collectors by which you can meet your requirement. Can you go for the next one, sir? So this is a very basic thing. So just to mention that you can have a flat plate collector. So if your temperature range requirement is around 30 to 80 degrees centigrade, it is a non-concentrating type, or like you can simply say it is a flat plate collector, and the application is solar water. So you can attain a temperatures of around average basis, it is around 30 to 80 degrees centigrade. Next one, please. Next slide, sir. If you further need to attain higher temperatures, next obviously this is linear Fresnel reflectors can be used. So you can see here there are flat mirrors which are placed on the ground, just above the ground, and each mirror will be orienting as per the location of the sun, such that the reflected radiation directly falls on the a receiver. So in this approach, you can get something like around 60 to 250 degrees centigrade, depending upon the concentration ratio. And especially this kind of solar thermal devices is used for power generation in general. Can you go for the next one, sir? And this is a parabolic trough reflector. And obviously, based upon the concentration ratio, you can still attain something like 60 to 300 degrees centigrade. And especially this is used for power generation. And next you have next one, parabolic dish reflector. So parabolic dish reflector. So here concentration ratios are further high, and you can attain a temperatures range of around 100 to 500 degrees centigrade. And this is generally used for power generation and cooking purpose. So next comes that heliostat based central receiver system. So depending upon the concentration ratio, actually this helio means it is the sun. Stat means stationary sun. Stat means stationary. Heliostat means stationary sun. So what happens to this is like each reflector will be tracking the sun, and it makes sure that all the radiation that is incident on this particular reflector will be focusing or concentrating on the receiver. So you can still attain the temperatures around like 2000 degrees centigrade, and with this kind of approach, we can use even have solar furnaces where we can melt metals also. So next one, sir. So the first one is because the power density is low, obviously you need to go for certain concentrating devices to meet your requirement. Another thing is conversion and storage. So whatever solar energy that we tap, obviously it can be stored in terms of batteries. Once you get electricity from the photovoltaic panel, you can directly store in terms of battery. Another thing is thermal energy storage. Obviously, you can have sensible heat storage, latent heat storage, and thermochemical energy storage. The picture that is given towards your right is thermochemical energy storage. So obviously, depending upon your temperature requirement, you can go for different techniques, different approaches. So generally, latent heat storage materials has some disadvantages. In the same way, sensible had some disadvantages, and in the same way, like thermochemical energy storage also have their own disadvantages. But obviously, a lot of work is being done on this. And when you need to attain very high temperatures, thermochemical energy storage can be a promising one. Especially in latent heat storage materials, you need to go for salt hydrates so that you can store thermal energy at higher temperatures. So can you go for the next one? So first two disadvantages we have seen how it can be overcome. Next, another thing is like the solar radiation is not uniform throughout the world. Like in some places you do have it is totally blessed, and some places it is in a very dilute form, and some places it is hardly available. So what you do is like just as I was discussing in this particular presentation, you can have hydrogen that is produced by tapping solar energy. Hydrogen can be stored in terms of like in cylinders, and these cylinders can be transported to wherever you are in need of power or energy. So one such thing is like have hydrogen, or like this hydrogen can be obtained from methane steam reforming, where methane and steam is combined, and you get hydrogen, and this hydrogen can be used in the fuel cell. So we did discuss three things. One is like solar collectors, how to tap energy. Another thing is like how to overcome this temporal variation of solar energy, that is by means of storage systems. Another thing is like because it is not uniformly distributed, you make use of you convert this energy, solar energy, into transportation fuels and supply as per your requirement. So in this way, like we do have a solution, and we can overcome these drawbacks that we have. Next one, sir. So if you see, now the question comes, I was discussing various other methods, and I did mention about green hydrogen. When you have hydrogen, hydrogen is produced without any CO2 emission, we say that thing as a green hydrogen. So you do have different methods by which you can produce hydrogen. One is solar electrochemical. What do you mean by solar electrochemical is you make use of solar energy and have a photovoltaic panel, and whatever electricity you get, you convert, use that electricity in electrolysis process and produce hydrogen. That is one. And another thing is photochemical. That means you directly make use of photon energy. And the third one is thermochemical. Can you go for the next one, sir? Here, what happens is you will make use of thermal energy by particular chemical reactions. What happens is you'll finally get hydrogen. So on the bottom, like in the like a half, like just in the bottom portion of the figure, if you see, I did give only thermochemical, various thermochemical process. One, if you see solar thermolysis, obviously you made use of hydrogen, sorry, water, and solar thermochemical cycles are there. And other things, solar reforming, solar cracking, or like in general, solar cracking is nothing but solar methane cracking. That is what we are going to discuss here. And another thing is solar gasification. If you just take the left portion, it needs like it is highly energy intensive. And right side, if you see from even solar reforming or methane reforming and solar gasification, you do have CO2 emissions. So solar cracking is one. You just make use of fossil fuel. Let us take, it can be a methane, and this methane, you directly in the process of producing hydrogen, you will not get any carbon dioxide. So that is why this methane cracking process is very promising, so that in this process of producing hydrogen, there is no CO2 emission at all. Can you go for the next one? In this methane cracking process also, as I mentioned earlier, whatever hydrogen that is produced now in the world, it is basically by methane cracking, steam reforming. So what is steam reforming? So you have a boiler. To this boiler, methane is added and water is fed, so that water is converted to steam. And this steam is exposed to natural gas in the presence of air, and you get CO plus H2. Let us take, you are getting syn gas. And by water shift reactor, you separate H2 and CO. But if you see the extreme left portion, in this process, You are burning fuel and you are getting hydrogen. So in this process, you have CO2 also. So if you see the middle one, whatever steam that is produced, you are using solar energy. But again, in this process, along with hydrogen, you have CO2 emission also. This is steam reforming process. Next, the third one is methane cracking process, where you design a reactor such that you expose natural gas such that hydrogen and carbon is produced. Please do understand this carbon, whatever it is there, it is in solid form, and you do not have any CO2 emissions in this process of producing hydrogen. So this is one of the very promising option, like a very good approach for producing hydrogen. Can you go for the next one, sir? So how it is going to happen? Actually, the reaction starts around 400 Kelvin and it completes around around 1300 to 1400 Kelvin. So if you can see the methane curve, as methane is dropping down, actually the hydrogen and carbon is there. So so you need something like around 1200 degrees C. The reactor temperature is around 1200 degrees C, so that methane can be converted to hydrogen and carbon without any CO2 emissions. Okay. So next one, please. So now the question is like, okay, everything looks very fine. So what is the problem? So there should be some device. What we coin is like a reactor. So this reactor, when you feed like methane, you should get hydrogen and carbon. So it is a necessary for us to design a reactor. It is like a heart of this particular process. So if your reactor design is good, obviously the productivity of this hydrogen is very fine. Like you have higher productivity also. So now what is the problem? So you can go for the reactor and you can get hydrogen. The problem with this particular process of methane cracking is this: when this cracking process is taking place, hydrogen is fine, but whatever carbon that is formed is a problem. So it reacts, it clogs to the reactor walls, windows, and so on, and it is leading to the failure of the reactor. Can you go for the next one? Actually, this is a video. I have this is a video. Usually, I just would like to mention this is a reactor. This is what we have designed, and we coined it as a aero shielded reactor. Actually, the results I wanted to present. You should be having a source file, sir. I think you cannot run it. I kept all the files in my folder, so that is why I'm able to run in my system. And its space is like very large. So otherwise, okay, we will continue with this one itself. Yeah, can you move it further? I think. Okay, go for the next one, sir. Uh, one more click. I will just explain with this particular figure. No, no, go back, sir. Go back. See, what is the problem with this process is, you can see there is an inlet, and through that inlet, you can see that upper left figure. So there is an inlet. What we do is we send methane. Along with methane, we inject carbon particles such that the reaction sites can be more, and you have more productivity of hydrogen. But the problem is when the solar radiation is exposed, this methane converts to hydrogen and carbon in solid form. So this carbon, whatever it is formed, it starts agglomerating near the reactor exit and reactor walls. Because of this, what is happening is the exit is getting choked, and if there is a pressure fluctuation, the reactor is getting blasted out. That means it is exploding. So that was the earlier animation what I tried to show. And now what they did is, this is an ETH Zurich group, which is ETH Switzerland. So they tried to design a reactor with this particular concept. And towards your right, one person is standing right. So back to him, it is solar simulator. So what does it do is, because especially in Switzerland, all the time sun may not be there. So to run the experiments in lab itself, that will mimic the sun. So they can have more concentration also, like more concentrated solar radiation also, which they can mimic. And towards the bottom left, you can see once this solar simulator is switched on, you can attain different intensity of radiation. And the front portion of the reactor is given towards right bottom. So the front portion is a cooling channel. So why? Because just in front of the glass reactor window, if you have very high temperatures, the reactor may melt. So that is why they need to have that cooling system also to take the to dissipate the heat out. Can you go for the next one, sir? So what they tried is to understand in actual phenomena how to do. There is a heliostat. This heliostat, which is of around 120 meters square, this tracks the sun, and it makes sure that it focuses on the concave portion. You can see just opposite to the mirror, there is one shutter kind of thing. So backside of the shutter, like blinds are there. Backside of that, there is a concave shape, like a mirror, huge mirror is there. And the focal point of this particular mirror, they place the reactor. So this heliostat tracks the sun, and it makes sure always it reflects this radiation on this concave portion, and this concave shaped mirror focuses all the radiation at the window of this particular reactor. So just to understand how can they have this reactor work. So this is what their experimental facility was. Can you go for the next one? This is a reactor which was developed by ET, like Weizmann Institute of Technology, Israel. So you can see towards your right. So they feed methane, and just to avoid melting of the window, they use window screening. So this window screening will help to cool the glass, and they just made sure there is a vortex that is formed, so that the residence time of methane can be more, so that you can have better protection for the hydrogen. But what it was observed is this is not able to work. So slowly at the exit portion of the cone, whatever vortex generator you are seeing right here, so that is getting clogged. So this was also not working well. So can you go for the next one? This is Israel's reactor, and there is NREL, National Renewable Energy Lab from USA. They could develop this reactor. You can see towards the right portion, left portion, the concentrated radiation will be made to pass through this concentrator, and all the radiation will be reflected to one particular point. That particular section is given towards your right. So from the top, methane is fed, and you can see here from the sides, hydrogen is swept, and there is a porous tube. This hydrogen will sweep these carbon particles which are coming towards this side, so that carbon and hydrogen that is formed along with unreacted methane can pass through this and go through the exit. But what it was observed is, so as it goes, like as the reaction starts, within no time, this particular center portion of this particular reactor is getting clogged. So that the and further methane is not able to convert to hydrogen. So this was also not working well. So can you go for the next one? This is CNRS France design. This design is very simple. So in this, they have like a two plates, and obviously in between they kept a separator. So from the top, solar radiation will be concentrated, and it is made to pass through this Pyrex glass. And you can see methane and argon, inert gas, is sent such that it can sweep the carbon particles. So this concentrated radiation will be falling, is made to pass through these particular plates, and through the plates they are sending methane. But what it was observed is, even as this methane comes in contact with this particular plate, the carbon, it is getting agglomerated and it is getting choked. This was also not working well. Can you go for the next one? So to search, like to give some solution for it, at Texas A&M, we worked on this particular problem. See, like if you go to a mall, shopping mall, at the entrance you have air curtain, right? So in the same manner, can we have like an air curtain such that this carbon will not go and stick to the walls of the reactor? That is what the plan was. So then we thought of designing some reactor in such a way that you have a very good cage-like structure at the walls, and this carbon particles agglomeration can be avoided near the walls. So this was the idea, and we started designing the reactor based on this particular concept. Can you go for the next one, please? So you can see here, this is the basic reactor. F1, you can see on the left hand side, F1 represents the main feed. That means through inlets, multiple inlets, methane is fed. And if you observe, these inlets are not straight normal, it is tangential, such that it can form the vortex. Why vortex is, if you have vortex kind of flow, the residence time can be large, so that you can productivity of hydrogen can be more. So on the right hand side B picture, you can see this is the front view. You have side walls, there is a screening gas, and for glass also there is a screening. Okay, so this side screening is just to make sure that it sweeps the walls, and it can avoid the carbon agglomeration. That is the reason why we proposed in this way. Can you go for the next one? So obviously, before going to experiments, because several things are getting failed, we did a thorough numerical study, and for that, because it has all the complexities in this world. Obviously, we do have turbulence, and we do have radiation, and hydrogen is fed. This methane is there. Methane is now converting to carbon and hydrogen. So there is a species transport, and obviously there are particles. So DPM model, discrete phase model is used, and obviously like the convective terms also becomes like very much significant. That is why we used second order Appling scheme. So finally we could solve this thing by applying finite volume method, and simple algorithm was used. Can you go for the next one? These are the governing equations: continuity, momentum, because it is RNG K-epsilon model, kinetic energy and dissipation equations are also there. Can you go for the next one, please? This is the energy equation, species transport. So go for the next one, please. And it is very important to have interaction between the fluid and the particle. So this is about like a particle interaction, and the drag also becomes very important. So particle Reynolds number and drag is also calculated based upon the particle. And there is an energy interaction between the particle as well as the fluid. And the bottom one is nothing but the energy heat interaction. That is like there is a thermal transport between the particle and the fluid. So that physics was also incorporated here. Can you go for the next one? So obviously, if you are doing some CFD simulation, validation is one of the very important things. So there was very less numerical work on this. So we have taken the work that was published by Israel group, and qualitatively we could compare the results. So for a particular set of simulations, what we could do is we could compare and could predict satisfactorily. So this is one particular validation. Next one, please. This is like an next one. So we have taken ETH Zurich reactor also, and we did see like we did compare the validation, and this is the temperature distribution of the reactor. You can see there is an inlet from the back portion, and we could trace like and we could understand like certain amount of fluid methane is going to the secondary reflector near the glass. So because of that reason, glass is getting burnt. So we could successfully compare our numerical results with the experiment results of Zurich group also. Can you go for the next one? So based upon this, whatever numerical methodology, after successfully validating our numerical methodology, we tried to apply this concept to our reactor, which is of a different kind, like which is unique. So you can see this is a hybrid mesh that we used, and from the sides in a tangential portion, we fed methane. Along with the methane, we fed we introduced carbon particles also, such that the reaction rate is high. And from the sides, along the circumference, we have like a wall screening, and there is a window screening from the top. This is the mesh of the reactor that we used. Can you go for the next one? So before actually doing the actual experiments, whether the residence time of this methane is very important, because it is not appropriate if we feed methane directly. It goes to the inlet and directly it comes from the to the outlet. So we have to design in such a way that it spends more time. Methanes can spend more time on the reactor. For that one also, we did like a detailed CFD analysis, and we modified the dimensions of the reactor such that the methane can spend more time in the reactor itself, so that we can have higher productivity rate for the hydrogen. So these are the results for that one. Next, please. Actually, there is an animation, but I'm sorry, I'm not able to show this. These are the results that we got after doing CFD simulations. So what it was observed is, we tried different gases, because when you feed methane, it is very difficult to separate this if you are using different gases. So first we tried with wall screening and window screening with hydrogen. But because hydrogen is relatively less denser, when methane is fed, this methane is sweeping the wall screening also. It is not giving a promising result. So then we tried towards your right. Actually, these are very good CFD results, but unfortunately, I'm not able to present here. And when I feed argon, because argon is like an inert gas, this is able to form a cage-like structure. And depending upon the gas that we are using, there is a significant influence on the end result. So when hydrogen was used as wall screening, the reactor is getting clogged within no time. But when argon is used as wall screening, the agglomeration of these carbon particles near the walls is very less. So this was observed like a perfect cage kind of flow, where this methane is not able to reach the wall. Can you go for the next one? So this is about like a temperature distribution. What we have observed is, when you go for like hydrogen wall screening, I could observe that there is more temperature near the walls, which led to the clogging of this carbon near the reactor walls. But when you go for argon wall screening, the temperature distribution is more uniform, and the productivity rate was very good. So this is one thing. Actually, this is also a result. We can actually see the animation of how the temperature is getting varied with respect to time. Can you go for the next one? And obviously, what we did is carbon concentration. If you see towards your left, when I used hydrogen wall screening, the carbon started agglomerating around the walls. So it started blocking the reactor. The reactor was like not was giving a satisfactory result. But for argon, you can see this jet. You can see case 2 near the circumference walls. There is one color variation is there. So this is providing some jet kind of behavior, because of which what is happening is the carbon is not getting deposited near the walls. So with this, but still what is happening is, after some time, the reactor is getting choked. So we are not able to understand. So we tried to, as I used a discrete phase model, we tried to see like where the carbon particles are going and hitting this particular surface. Can you go for the next one? So actually what we did was like if you take any carbon sample, it is not like mono-sized. You do have a particle distribution. So this particles, whatever sample that we have, like a Fluka 05120 is the sample. Like we tried to use particle size analyzer and got the particle size distribution, because they will simply give the average particle diameter. But usually if you take any nanoparticles also, there is a particle size distribution will be there. So we tried to understand by taking the particle size distribution in this particular way, by feeding this carbon sample in particle size analyzer. So we can get distribution in this way. Can you go for the next one? So what happened is we tried to see like do a very good parametric study, like flow rate, main flow is varied, window screening is varied, wall screening is varied. And if you observe extreme right, there is window deposition and exit deposition. If you see, when argon is used as wall screening and window screening, this second column from right, the window deposition is nearly zero, especially when argon is used. But exit deposition is more, like it is relatively more when compared to the wall screen, like when compared to the window, but exit portion is getting clogged. So we are not able to understand what is the reason behind it and so on. So can you go for the next one, please? So we did like a very detailed analysis and tried to understand the influence of each and every parameter. Can you go for the next one? So if you observe, whatever blue lines are there, those are methane. And wall screening, red, that if you see like wall screening, it is argon. So, but what is happening is, if you can observe, both the cases when wall screening argon is used, it is giving a very good cage-like structure. Whatever red is there, that is argon flow. So this cage-like flow structure is protecting the reactor such that the carbon particle is not going and sticking to the walls. So, and one more thing, the residence time of this methane is also is more. So, but still the reactor is getting clogged. But that is why then we started exploring further. Can you go for the next one? You can see this particular picture will tell you, see there is walls, it is clear, and but exit, especially when the flow rate of methane is more, you can see more amount of carbon is getting choked near the exit. So and what is the problem behind it also we need to analyze. But both the cases, the reactor is getting choked. That means reactor is getting clogged at the exit. But walls, we are able to get a solution. So what is happening is like we try to further analyze what is happening and why do you think like the reactor clogging is more when you have a higher flow rate. If you can see for 20 liters per minute, the reactor clogging is taking at a faster rate. Then we further try to understand how the particles are moving inside this particular reactor. Go for the next one. Can you change the slide? Next slide, please. See, we try to understand depending upon the particle size, does it make sense or not? If you can see, for smaller flow rates, like you can see like it is going directly like this, like you can see different colors, and left hand side will give the particle size distribution. And if you see towards the right hand side figure, and if you observe, when you go for higher flow rates, the larger sized particles are leading this problem. This is causing the problem. So it is going and hitting the walls, and it is getting agglomerated near the walls. So what we thought is, can we, if we are able to reduce the particle size, can we avoid this problem? So then what we did is, instead of going for a larger sized particles, we tried to go for a mono sized particles. Like means it is very difficult, but does it have an effect like that? We wanted to see. Can you go for the next one? So based upon this result, what we have observed is if instead of going for like a larger sized particles, we have taken the supplier details. He mentioned that is like a 40 microns is the average particle size. So instead of giving the particle size distribution, we tried to take only mono size of 40 microns. Why? Because in the earlier picture we could see like larger diameter particles are the reason, because it does have more inertia, and because when you have a higher flow rate, it is going and sticking to the walls. So because of that reason, we even tried this one, and it is observed to be very promising. So, but practically maintaining 40 microns is very difficult. So it does have a lot of constraints. But in case like if we are looking for a solution, obviously this is one particular approach that we can go for. Can you go for the next one? So finally, what we can observe is when argon is used as a window and wall screening gas, a curtain-like shield is observed through the walls. Actually, this is protecting the walls from clogging of the carbon. But what is happening is when you use hydrogen, actually that is more useful for us, because again, once at the exit, there is no need for us to separate argon, hydrogen, and so on. But this was not working well. So if you want to use like hydrogen as a window screening gas, that is not working well. So that is ruled out. Why? Because you have higher deposition at the exit. Can you go for the next one, please? And further, what we can do on this one is, if you can fine tune the reactor exit further, then we can still, and parallelly the reactor exit is again function on the vortex kind of flow that we have, and again like cage like structure near the walls and so on. So obviously a lot of work is still pending uh, to further explore in this particular area, because I did explain like why this green hydrogen is very important. But the problem with this one is whatever methods that we have been following, it does have like several issues. So one such temporarily, like one such solution that it can be given is, so if you can operate at lower flow rates with a mono-sized carbon particles, then you can have a promising solution to have green hydrogen. So I think that's it from my side for this presentation. If you have any questions, you may please type in the chat box. Sorry, actually, it was initially working well, but I don't know what problem was it. Yeah, if you have any questions, I am not able to hear from anyone. You may please type in the chat box. All the members, I'm able to see only mute. All the members are like in a mute position. I don't know what kind of technical issue.
Yes, sir. Thank you, sir. The participants will
So
post
you
the
may
questions
please
in chat
type
box.
in chat box if you have any question, please.
Participants, if you have any questions, please post it in the chat box.
Actually, this is one method, but several other methods also are being explored in hydrogen production. And all the countries, all the research institutes around the world are seriously looking for green hydrogen. This is going to be one of the very prominent area to work on. And this is going to be future also, at least for coming 10 to 15 years or so. This area is going to be like very, very important. So those ever who whoever wants to do some research in any new areas, I can say this is one of the best area to work on, especially anything related to energy.
From participant side, if you have any questions, please post it in the chat box.
Otherwise, unmute your audio.
Sorry, I'm not able to hear from anyone.
Hello? Hello?
Sir,
Hello,
tell me,
sir.
sir.
Madam, before going to question answer sessions, please ask all the participants to switch on their videos.
Okay,
After
sir. Okay,
taking the
sir.
photo, then we can go for that. Okay?
Okay, sir.
Sorry, I could see some some of the things are getting activated, but I could not hear anything. So you may please type in the chat box.
Requesting all the participants to unmute your.
All the participants are requested to switch on video for 30 seconds.
All the participants are requested to on
Please
the
switch
camera.
on your video.